Welcome back. Today we will be talking about the exponential and logarithmic function. So the parent function for the exponent is f of x is equal to e to the power of x, as you can see from this whole entire notes. And when we are talking about the exponent which is x, uh, it is nothing but the all real numbers. But the main thing that you need to focus on is this, that the a, which is the base, should be greater than 0, and we are not looking for it is equal to 1. So what is acceptable and what is not? I have given you the list. We are not taking a as a negative or a as 1 or 0. So as I said earlier, the domain is all real numbers. When it is decreasing, the function will look, the graph will look on the left hand side. With the increasing function, we have a graph on the right hand side. So y will be greater than 0. Asymptote will be at x is equal to 0. So what do you mean by asymptote? The graph will seem to touch the x-axis, but it will never touch the x-axis. So be careful when you're graphing the exponential function. To solve the exponential functions, we have some strategies. If we have the same basis, so we don't need the basis, and we can put the two exponents equal to each other. As you can see in the example, I can write 9 as nothing but 3 squared. Now the bases are same, I don't need bases, so I can put the two exponents equal to each other. Same thing with question number B. The another thing that we need to keep in mind is the exponential in the standard form. For the standard form, the transformations that you have learned in Algebra 1, that is the same thing. In this case, C is a horizontal shift, and remember, negative of a to the power of x is not same as negative a to the power of x. So the transformations will remain the same as you have learned in Algebra 1. Now f of x is equal to e to the power of x is called the natural base. E is in many pronunciation they call it as Euler's number or Euler's number. So the spelling is E-U-L-E-R, and the number is something like this: 2.71828, 1828, and so on. So why we need the exponential function? E is a number, and we will not plug the number for E. It can be written in this form. It is a continuously. It is derived from the continuously compounding. So 1 plus 1 over x to the power of x. Basically, this is the function that is the meaning of E. As it approaches, as x gets bigger and bigger. So as x approaches to basically to infinity, and if this function is there, that is nothing but E. That is basically the definition of E. So E is limit as x approaches to infinity. Then we have 1 plus 1 over x, the exponent x, that is nothing but E. So keeping the E as exponential function, we have to keep in mind that x approaches to infinity. So 1 over x approaches 0, because any number divided by infinity is nothing but a 0. So we are getting limit as x approaches to infinity is 1 to the power of infinity, because 1 plus 0 is 1. 1 to the power of infinity, that is nothing but our number E. Because remember, any number divided by infinity, because in denominator is getting so big that it is nothing but a 0. So E is equal to 1 to the power of infinity, which is nothing but 2.718, and we can, and this is just for understanding. We will focus more on f of x is equal to e to the power of x, and from there we can apply various strategies to solve it and graph it. Now let's talk about compound interest. So we have discussed about the compound interest earlier as well. Basically, there are two ways we can calculate the compound interest. So when we are talking about the compound interest, we are saying P in the parentheses 1 plus r divided by n to the power of nt, that is the amount. So what are p, r, n, and t? Let's understand it. So A is nothing but total amount, then n is number of time the interest is compounded, then t is time in years, for how many years you want to compound the interest, and r is rate of interest, and p is the initial or principal amount or your initial investment that you started the amount with. Keeping this thing in mind, when we say compounded continuously, we use A is equal to PERT. That means P times E to the power of RT. Now E here, as I explained, is nothing but the exponential. So that's why I tried to help you understand that E is nothing but 1 to the power of infinity, because we are compounding the interest continuously. So in other words, amount is limit as n approaches to infinity. So when we approach it to infinity, the initial formula for compound interest, that becomes compounding continuously, because infinity implies it is repeating again and again. Let's take some example. So if we say principal amount is 10,000 at 3% rate of interest for 10 years time frame, and let's take the first case as compounding annually. So annually, that implies t is what? T is 1 year. So t will be 1, p is 10,000, r is 0.03 divided by 1, because we are compounding it yearly, n is 1 to the power of 1 times 10. And then you can plug it in the calculator and you will get the amount. So the amount will be 13,439 and 16 cents. So 13,439.163. So keeping that in mind, let's try to find compounding quarterly. So quarterly implies what? That in 1 year you are finding the rate of interest 4 times. That means n is 4, r is 0.03, p is 10,000, and t is 10, but n is 4. Compounding daily, that means n will be 365. So quarterly, daily, what will change? Only n will change. Now if I say compounded continuously, remember, for compounding continuously we are using PERT. We are taking the same principal rate and time. So 10,000, it will be 10,000 times e to the power of, rate of interest was 0.03. So 0.03 times 10. And then just plug it in the calculator and you will get the answer. But before you put in the calculator, you might need to adjust the exponent. So the answer will be 13,400 98 and should be 0.5 something. It should be a decimal after 8. So again, we have two formulas. A is p times 1 plus r over n to the power of nt, and the another is compounding continuously. The another type of question that could be there um, with these concepts, it could be radioactive questions. So for the radioactive questions, so radioactive decay, there are certain things that we need to keep in mind. A will be p times r to the power of T over n. So we are looking for another formula for radioactive decay. So R is rate of decay. Then we have T as time, N as how long it takes for that to decay or for that to happen. So P is nothing but the initial or what we are starting with. Or the total left. A is nothing but the total leftover. So what will be the total leftover after the decay has happened? So keeping these parameters in mind, let's try one example. So we have something. Plutonium's half-life is given as 24,100 years. And the question is asking you how much of 8 grams remaining after 100,000 years. Okay, so let's try to see what is given in this particular question. So what is half-life? Half-life is nothing but the rate. Then 24,100 is n, and 8 grams is nothing but p. So let's put everything in the formula, and 100,000 is time t. So solution. So I want A is equal to 8 times, in the parentheses, 1/2 to the power of time, which is 100,000, divided by n. N is nothing but 24,100. So it is my suggestion, first simplify what is 100,000 divided by 24,100, and then use it as the exponent. So if you do the calculation and put it in the calculator, you should get the answer as 0.45 grams. So that is what will be left. Or you can say still dangerously radioactive. That is how you will solve the radioactive problems related to these exponents. Now, let's talk about the characteristics, some basic characteristics. So it will sum up whatever you know from about the exponents from X-rated algebra 2 or algebra 2 and from algebra 1 as well. So we are talking about the characteristics of y is equal to a to the power of x graph. So let's talk about the domain. Domain will be the whole entire number line. That's what I said earlier. Range will be 0 or greater than 0. That means up to the infinity. Y-intercept will be 0 and 1. We are talking about the parent function here, right? And the horizontal asymptote will be at x is equal to 0 or just x-axis. As x approaches to negative infinity, a to the power of x approaches to 0, right? Because we are talking about the positive function here. So these are the basic characteristics of a to the power of x. Bye-bye.